The third video in this series describes a progression of catalysts from the Grubbs 1 precatalyst with two tricyclohexyl phosphine ligands. In the late 1990s, Grubbs and several other laboratories reported replacing one of the phosphine ligands with an N-heterocyclic carbene, which is a neutral 2-electron donor ligand, with the carbene stabilized by resonance delocalization with the non-bonded electron pairs on the nitrogens. To replace the second phosphine, which was thought to inhibit reactivity, Hoveda's laboratory came up with the idea of an ortho-ether substituent as a coordinating ligand that would be covalently connected to the carbene ligand in the precatalyst. The Hoveda-Grubbs precatalyst is particularly popular because it is quite stable to air and moisture, but acts as an effective reactant with alkenes. Grubbs was also particularly interested in developing a precatalyst that would favor Z-alkenes or cis-alkenes. In the most successful of the Z-selective precatalysts, one of the aromatic rings on the N-heterocyclic carbene has been replaced with an adamantyl group, which itself acts also as a secondary alkyl ligand, replacing one of the chloride ligands. And then the second chloride ligand is replaced by a nitrate anion, in which two of the oxygens of the nitrate will coordinate to ruthenium. We used this catalyst several years ago for a cross-metathesis process. Cross-metathesis involves interchange between two different alkenes. In most cases, cross-metathesis will require an excess of one of the components. In our application, the component in excess was not only the less substituted alkene that would preferentially initiate the catalytic cycle with ruthenium, but it was also more easily prepared. The alkenyl alcohol is commercially available, and so we simply had to add a trimethylsilyl group, whereas the epoxide substituted alkene required several steps to prepare. Although we never optimized the yield of this transformation, we did see high selectivity, 9-to-1, favoring the cis isomer using the Grubbs precatalyst. The way that we conducted this reaction was to mix the components together in tetrahydrofuran and then attach the flask to a rotary evaporator in a warm water bath, 35 degrees Celsius. The rotary evaporator, under approximately 7 torr of vacuum, gave us the best cis selectivity. In class, I'll ask, how do you think that running this reaction with 7 torr vacuum, which is about 1/100th of an atmosphere of pressure, can help this reaction? Moving down the page, I'll show the catalytic cycle, at least a partial catalytic cycle. The active catalyst is the ruthenium methylene carbene, which undergoes ligand association and cycloaddition to give the metallocyclobutane shown here. This does a retrocycloaddition, produces ethylene as a byproduct, and then a second molecule of alkene will associate with ruthenium, forming a metallocyclobutane, and then this does a retrocycloaddition to to give the cis alkene. Based on the evidence that we get a 9-to-1 ratio of isomers favoring the Z alkene, what is the reasoning supporting the claim of at least 3 different structural elements of this catalyst? One of those claims may be the bulk of the trimethylphenyl substituent. Another one of the claims is that the nitrate ligand is key for replacing the chloride. And a third aspect of the claim is having the adamantyl ligand, which serves as an alkyl ligand for ruthenium and a substituent on nitrogen on the N-heterocyclic carbene ligand. This concludes the video on Z-selective alkene metathesis.